All right, guys, this is just the first problem from each of the different sections on solving or factoring or solving by quadratics by factoring. So this is the other really big idea that we spent a good portion of this semester on. And so super important. It'll be on the little Google form quiz for the end of the year assessment. So I want to go over one of each problem, and then you can try the other two for practice. One thing that's nice about factoring is that there's a built-in check. I'll show you how that works here, but the check is to multiply, because multiplying, or using FOIL in some cases if it's a binomial times a binomial, is the inverse operation of factoring. So this first one is called a difference of perfect squares, and it's got a 36a squared as the first term, and a 25 as a second term. It's a difference because it's got a minus sign right there. 25 and 36a squared are perfect squares. The square root, you just take the square root of 36a squared, which is 6a, and you take the square root of 25, which is 5, and that means the factors are 6a plus 5 and 6a minus 5. And the way you can check all of these factoring problems is by multiplication. In this case, I can use specifically our acronym FOIL because it is a binomial times a binomial. FOIL, F-O-I-L, has 4 letters in it. We use it only for binomial times a binomial because you will have initially 4 terms. The first term, 6a times 6a, gives me 36a squared. The outer terms, which are 6a times negative 5, is negative 30a. The inner term, you move this I over a bit and the L over a bit. The inner term will be 5 times positive 6a, which is positive 30a. And the last terms are 5 times negative 5, which is negative 25. And what you can see is if you were to go and combine the like terms here, the outer and inner terms cancel to equal 0, and you're left with the original problem, 36a squared minus 25. So this technique applies to all problems in this row on your practice handout. And I'm not going to do every one. You can check them yourself by using FOIL to multiply them out, or the distributive property. Number 4 is one where you might not factor it completely, and yet it would check out. GCF first. If you take out the greatest common factor first, that's the way that we go about completely factoring something. We're going to notice, and that's what we should check for every time first. I should have checked for that on number 1, but it's a visual check for me. I know that there is no GCF other than 1 that goes into 36a squared and 25. But on number 4, I can quickly see that 2 will go into both 2a squared and 18. So if I factor out a 2 and then write what's left over when I divide each term by 2, 2a squared divided by 2 is just a squared, and 18 divided by 2 is negative 9. And now I'm left with a 2 outside, so I have the 2, but then I also have a difference of squares left to factor. The a squared is a perfect square, 9 is a perfect square, the square root of a squared is a, square root of 9 is 3, so I have a plus 3, a minus 3, and that's what we consider completely factored quadratic, because we have factored out the GCF first, and then applied factoring principles to whatever's left over and factored it as well. Okay. As I move into number 6, I can quickly and easily see there is no GCF other than 1. It's definitely not going to be a difference of squares because I don't even see perfect squares. Like 27 is not a perfect square. I guess the 1x squared is a perfect square. The 27 is not. But it's not a difference of 2 perfect squares because there are 3 terms. This is in fact a trinomial. It's going to factor as 2 binomials. What we mean by the big X, students, you guys could explain this to your parents and how the big X works. I have taught algebra to adults at Folsom Lake College, and they just love this method. and that it's showing up as a little math arithmetic game in elementary school too. So a lot of teachers and students are being introduced to the X method, or whatever you want to call it. There's lots of different names for it, but it's just a way of thinking about what are the factors of C, which is the last term in standard form of the trinomial. So C is negative 27. What are the factors, or two numbers that multiply to equal C, or negative 27? And I really should, just as I'm building for number 9 here, it's really A times C. So in this case, A is 1. And so it simplifies down to, we are just looking for factors of C. But in general, for a quadratic trinomial, we're looking for factors of A times C. So that's what goes up in this spot. A times C is up here. That add to equal B. And B is the middle term there. It's the term in front of the linear variable X. So they have to multiply to equal negative 27 and add to equal 6. So, you know, some students, some of you guys are able to just look at this, quickly come up with the two numbers that work. You see that the 9 and 3 are going to work. You just have to play with signs. Others don't see it. What I've encouraged you to do is, if you don't see it immediately, just start with 1 and 27 and then start doing division. You could have your calculator out. Do 27 divided by 2, and then by 3, and then by 4, and then by 5, until you have listed all possible factors. You know, in Algebra 1, we don't give you too many non-factorable or prime quadratic trinomials, but it could happen. As you move on in mathematics, we want to make sure that we have a method for deciding if this thing can even be factored in the first place. And so we have to think of all the different possibilities here. I could try 4 into that, 5, 6, 7. I'll keep going until I get to 9 and 3. And then I've just flipped and reversed. You know, I'm going to have the same, I have 9 and 3, and then 27 and 1, which are essentially the same factors. Now, those are the only two pairs of factors. What we're looking for in this case is two factors that have a difference of 6, because one of them is going to have to be negative and one of them will be positive, so that they multiply to equal the negative 27. So I have a negative 3 here, a positive 9. Those multiply equal negative 27, and they add to equal 6. Now, for those of you students, when we talked about factoring quadratic trinomials, and I'm once again trying to think about what's coming next here on number 9, we talked about the fact that you have to then divide by the coefficient of the squared term, or the A here, and then simplify those. Now, of course, in this case, we're dividing by 1, and so it was already simplified when we had the negative 3 and the positive 9 listed here. So it was already simplified. And those are my factors. So I just pair each of those with the variable. So I have x, whoops, try that again. So I have x minus 3 and x plus 9 as my two factors. And if you use the distributive property, multiply those out and simplify, you'll get x squared plus 6x minus 27. That's why I have the equal sign here. Okay, now let's show how the big X applies to a not so simple quadratic. That's a quadratic trinomial where A is not 1. A in this case is 3, B is 14, and C is 15. So there's just an added step over here. We're still looking for factors of A times C, which in this case is 45, that add to equal B, which is 14. We're going to list all of our factors. We've got 1, 45, 2, no, 3 goes into it 15 times, 4 does not go into 45, 5 goes into it 9 times. We see that that's the one that works. 6, no, 7, no, 8, no, 9 goes into it 5 times, and we start repeating the list. So those are all my factor pairs, as we call them. Now this time we're looking for factor pairs that add to equal 14. We don't need to worry about them multiplying to equal a negative number. So we just need two numbers that multiply to equal 45, add to equal 14. You don't have to use the big X to be able to find numbers that multiply to equal A times C and add to equal 14. It's helpful, especially in a case like this. So what we're going to do next here, and this relates to we talked about, why this works when we talked about solving quadratics in chapter 9. But we're going to divide each of these side numbers by a and then simplify. If you do not simplify, you'll have extra factors in there. It will not work. So 9 divided by 3 is 3. 5 over 3 does not simplify. We called this bottoms up in class because the bottom number comes up and is paired with the variable. So I have 3x plus 5. Some students will even put the x down here on the bottom. You could have done it on all these if you want. But don't forget to simplify. So 3x plus 5 and x plus 3 are my two factors. All right, next one here, number 12. We're going to factor out a GCF first. After I factor out the greatest common factor, you will see that I will be then applying the x method here. So the greatest common factor here looks like it might be a 4. If I pull out a 4, dividing 12x squared by 4, I get 3x squared. 20x divided by 4 is 5x. And 8 divided by 4 is 2, and we have a minus sign there. So I have to check and see. I could be done at this point. It would just point out a 4, but I have to check and see if that 3x squared plus 5x minus 2 might not factor more. So I'm looking for factors of, once again, a times c, so negative 6, that add to equal 5. I know my factors of 6 are 1 and 6 and 2 and 3. Those are my only choices. Because I need to get a negative 6, I need to have different signs. So I know 2 and 3 add up to equal 5, but they have to also multiply to equal negative 6. So a 1, negative 1, and a positive 6 will multiply to equal negative 6 and add to equal 5. So those work. I'm then going to divide through by 3, which is the new a after I've factored out the GCF of 4. And so this one right here, 6 over 3, like that, simplifies to just 2 over 1, or just 2, and the negative 1/3 is already fully simplified. So my factors are 4, don't forget the 4, it's already been factored out. By bottoms up, I've got 3x minus 1 is another factor, and then 1x plus 2 is the other factor. So we really see this as 1, 2, 3 factors in the fully factored, completely factored form here. All right, some more special cases here. This is actually called a perfect square trinomial. You can see that x squared is a perfect square. 100 is a perfect square. If you multiply the square root of x squared, which is x, times the square root of 100, which is 10, multiply those two together and double it, you will get the middle term. And that is what must be true for any perfect square trinomial. So, if you didn't see that, you don't remember or don't recognize perfect square trinomials, this falls into the same category as the previous ones we've just done. You could do a big X on it if you want. You could look for factors of 100 that add to equal negative 20. And you'll notice that the factors are the same, and they are both negative 10. So if you recognize it, this is a special case. It is x minus 10 quantities squared. In other words, you have two factors that are exactly the same. It's a perfect square because if I were to draw a square with an area of x squared minus 20x plus 100 in the middle, the dimensions would be x minus 10 by x minus 10. Just like a square of area 25 has dimensions 5 times 5. So this is just an algebra lingo. We have a perfect square trinomial. The whole purpose of learning to factor here, was well, one of the purposes I should say, but a big idea for learning to factor in Algebra 1 is so that we can solve quadratic equations. Solving a quadratic equation is equivalent to finding the places where the parabola, which is what a quadratic equation looks like when you graph it, crosses the x-axis. So you are literally finding these places where the parabola crosses the x-axis. Okay? So go through the same process. This one is a quadratic trinomial. We're looking for factors of negative 14 that add to equal negative 5. They are -7 and 2 because those two multiplied equal -14, add to equal -5. That means, if I were to rewrite this right here, that means that I have the following factorization: x minus 7, x plus 2 equals 0. That's how we would factor that. And this factorization, along with what's called the zero product property, which says that if you have a product of two numbers and it equals 0, either one or both must equal 0. So we're going to set each one of these factors equal to 0 and solve for x. Super simple. This goes back to the very beginning of the year. Just add 7 to each side to solve this one. So x equals 7 is one solution. You'll notice, and you can try it on your own, if you plug 7 into this original equation, you will get 0. It's called a zero of the equation, or a root, or an x-intercept, or a solution, all kinds of different names for the same thing. If you subtract 2 from each side over here, you'll get x equals -2. If you plug in -2 up here to this quadratic for x, you will get 0. So those are our two solutions. We solve that by factoring. Okay. All right, the last one on here, see if I can put this down a bit, is just a slightly more difficult factoring problem. We're looking for factors of, remember it's a times c, -4, that add to equal 3. And they are +4 and -1. Don't forget, because this is not a simple quadratic. In other words, the coefficient of the squared variable is not 1, it is some other number. We've got to divide each of these by that number and then simplify. 4 divided by 2 is 2. -1 over 2 is already simplified. So my two factors are a plus 2 and 2a minus 1. Just check it. A times a is 2a squared. We've got a 4a in the middle and a -1a from the outside. 4a and -1a add up to equal 3a. And then 2 times -1 equals -2. So I factored it correctly. I did my little multiplication to check it. And now I'm going to set each factor equal to 0 and solve. So I've got subtract 2 from each side. A equals -2 is one solution. This one, add 1 to each side. 2a equals 1. Divide by 2. A equals 1/2 is my other solution. So that's factoring with the purpose of solving a quadratic equation. So I hope that helped. Should be ready to try that little short quiz on factoring and solving quadratics after you've practiced the other problems on this page.